contains 95% of the acetone. Okay, so you can find the top product, that is V, and that should be 15,000 maximum I'm talking about. Otherwise, we need to consider 0.75 also. Okay, as turn down ratio. So 15,000 into 0.04 divided by 0.95. So it is coming as capital V. I hope you understand all these balances that you must have read in your mass transfer course. And here I'm having a reflux ratio. We are given as uh, R by R plus 1.6 actually. It is so in this way we can have this R by R plus 1. That ratio is the slope of operating line. Okay. Yes, and here also we need to design the bottom plate. Okay, but this we need to consider L R by R plus 1. That is slope of top operating line from where you can find out this reflux ratio, and then you can find out this capital V. Okay, sorry, this is nothing. This is not the vapor. This is the uh, top product, distillate. Okay, so from this distillate, we can find out capital V 1578.9. Bottom product you can find by simple making the mass balance, and slope of operating bottom operating line 4.58 is given. Making energy balance, you can find out Vm prime and Lm prime. Okay, all these are maximum values. And once I'm having these flow rates, we can start the column diameter calculation. And here again, we need to consider top and bottom both. Okay, not the bottom only. So all these slopes are and parameters are given. So FLV we can find. Okay. Now your plate spacing is given as zero point 0.6 meter, and from here FLV for top and bottom you can find out K1 for top and bottom following this zero point 0.6 line. Okay. Now once I'm having this, we need to consider the correction factors, and correction factor should be correction factor should be one first it is for hold to active area 8%, and second is for surface tension different value. Okay, so you can consider a revised K1 value at top and bottom, and after that you can find out the flooding velocity in top and bottom, considering 85% of flooding velocity as the vapor velocity. You can find out vapor velocity in top and bottom, that is that you can see over here. Okay, now again we need to consider the um, volumetric flow. So maximum volumetric flow for top and bottom both we need to consider, and we can have the values of volumetric flow of vapor like this. Then net area we can calculate, which is coming like this. And again we are considering downcomer area as 12%. You can find top and bottom like this, and so the column diameter, which is coming as 0.83 meter, 0.84 meter almost. Okay, so this we will choose. Okay, let's say if you have been asked to find out the top, to design the top plate, then also column diameter will be, you can choose here this one value, this value only. Okay, so like this you can consider, and we will proceed towards the liquid flow pattern. And for that bottom liquid flow you need to find, you can see over here. And once you consider this 5.3 here and like almost 0.83 the column diameter, so somewhere you will again fall in cross flow or single pass uh, pattern. Okay, after that the column diameter is given average what we can say column. area we can find out, and then we can have downcomer area, net area, active area, and all that you can find out. Okay. LW by DC you can find, so wear length should be 0.64 like this. Okay, from this graph. I don't think that I need to explain this further. We have already discussed. Okay. Now we need to take the wear height as 50 mm, the recommended value, column diameter 5, plate thickness 5, all these you can choose. And area of one hole you can find out like this, 5, considering 5 mm. So number of holes should be 1712. So instead of 171, sorry, it is coming as 1712.79. So instead of 1712.79, you need to consider 1712 only, not 13. Please keep that in mind because diameter is fixed. Okay, so 1712, we need to uh, round down or round off the number of holes, right? Next, we need to find out for entrainment, and entrainment maximum velocity by net area, that you can find like 3.35, and FLV is coming as 0.1215. FLV from where you have taken? I hope it is clear to you. Okay. FLV, we can take this one, 0.125. Like this. And psi value you can see from the graph. Okay, this graph is given for a given FLV value. And here percentage flooding, you need to consider 85% only. We have not changed the diameter value once we have calculated that. Okay. Right. Okay, so we can have this psi value, which is well below than 0.1. So that entrainment condition is satisfied. Further, we need to calculate we need to check the weeping condition. And for that, you need to consider the maximum liquid flow rate at bottom, which is this. Okay, so this mass flow rate you can find, and maximum liquid rate at 75 turn down. So sorry, minimum liquid rate is 0.75 of this, so that is coming like 3.848 kg per second. Okay, we will calculate maximum HOW and minimum HOW. Maximum HOW will not be required over here, but you can calculate. That will be required afterwards. Okay, we need to consider minimum HOW, and that is coming as 25.49. And then we can have all minimum rate as 75.49. And based on that, you can find out K2 value. Okay, from this graph. So K2 is coming as 30.7. UH you can find as the 14.749, and actual flow rate, minimum flow rate. This is for bottom, VM prime into 0.75 divided by whole area. Okay. And then you can consider this whole area, how you have obtained. That should be, I think 8% is it is given. So 0.08 into active area. Okay, so this is already coming more than this, so we are moving in the right direction. Okay, next we need to find out the perforated area, where LW by DC you can consider theta C, you can find from this graph. Okay, and angle subtended at plate. Okay, this theta C we have calculated. So unperforated strip, that is it is coming as that it is coming as 180 minus 102. Okay, so this what is the point to consider over here? Just let me explain. Let me explain. Okay, 102 is this angle, right? Just a minute. Just you can see over here theta C is 102. What is this 78? 78 is basically basically this. What is happening? Just a moment. Okay, I think you can make that. You can understand this angle. Okay, this angle is nothing but the 78. Okay, and that is required to find out this area. Okay, so that you can consider mean length of unperforated edge strip. Okay, that is column dia minus 50. Actually, we are considering this length. Okay, so that should be pi DC minus 0.5 DC minus 50, because we need to consider the mean length. That's why we this thickness is given as 50 mm. So we need to consider the mean value of that. So DC minus 50 into 78 by 180. So this length is coming as 1.0618. Okay. So area should be 50 mm into this, 50 mm into this, like this. Okay, that you can consider. Hmm. You can say, you can argue that this area, whatever is given, and here also I'm having the unperforated area. Okay, so here if you see, instead of 360, we have considered 180. So twice we have already done. Okay, so area of unperforated edge strip, which is found is computed as 0.053. Mean length of the calming zone, that is 0.83. It is not 0.79. This is the previous diagram I have used, but it should be 0.83 minus 50 to find out this mean length. Okay, into sine 108 by 2. Okay, into this, because we need to consider this distance. Okay, so this distance we have taken as this mean length, and area of calming zone is twice of this length into thickness. So 0.0606 meter square it should be there. Okay, so in this way you can find out um, the calming zone area, and once you have done that, you can find out perforated area, that is active area minus uh, that area of calming zone and unperforated strip. Okay, so AP you can find by this, AH by AP you can calculate as 0.1095, and LP by DH you can find as you can find like this, which is coming as 2.8, and that should be between 2.5 to 4. Okay, so LP you can find as 14 mm. Now once you have this 14 mm, that should be the tube, that should be the whole pitch. Okay, so in this way we can find out the perforated area, and now we will proceed for plate pressure drop. Just a few minutes I will take to complete this. Okay, so maximum vapor velocity through the holes you can find like this. Okay, this you need to find out HD. Okay, and this AH by AP you can consider as this. Okay, plate thickness, hole diameter, that you can find, and then you can have CO value from here. Okay, AH by AP you can find, you have already found, and CO you can find as 0.85, HD you can find as 120.97 mm. Okay, this expression we have already discussed, and residual loss we have to find, and then total pressure drop, HT we have calculated. And once I'm having this pressure drop, we can proceed towards column diameter. Sorry, we can proceed towards the downcomer backup. For downcomer backup, we need to consider HAP which is 40 mm, and then area under the apron you can find like this. Actual downcomer area is this, so you can choose the lower value among these two, and considering this lower value, you can find out HDC as this value. So total HB we can find by this expression HW, HOW, then this is HD and this is HDC. Okay. So it is coming as 0.3 and 0.303, and that should be lesser than this plate spacing, which we have taken as 0.6, and weir height that we have taken as 50 that you can see. So this condition is satisfied. Next, we need to find out the residence time in downcomer section. So that expression we have all discussed a few slides back, and it is coming as 3.79. This is the expression. It is already given, right? So 3.79, which is more than 3 seconds. So in this way, you can find out the residence time, and you can have the all calculations related to plate design. Okay, so in this way we are stopping over here, and that is all about distillation column. That topic is already done. Okay, so that's all from my side for today. If you have any confusion, any observation, you can share. And please go through this design again in book, because it will be complicated. It's not very simple. Okay. So I hope it is fine. And uh, if no observation, no question is there, then I'm just stopping this lecture. So thank you everyone for your patience. Thank you.